Go. All right. So what we've got over here is we have a graduated cylinder with some water in it.
Mm-hmm.
We've got a spring scale, and we have a 1 kilogram mass.
Nice paperclip.
Yeah, I spent some time doing that yesterday. So, and what we're going to do is we're going to lower this into the water until it's fully submerged.
Okay.
Now the question is, what measurements could we make before we dump it in the water?
So we could measure the mass on the scale, right?
Well, okay. Let's write this down on one of those whiteboards.
Oh, they're over here. Whiteboard.
Sweet.
And then pen. I'm gonna grab a few because
I'm sure to
they
work.
tend to not work when I need them to work.
All right, so we could.
Okay, so mass.
So the mass
Uh-huh.
is 1 kilogram.
And then we could do the weight.
Okay, and the weight here.
Are you gonna call it 10 or 9.8?
9.80
Yeah.
newtons. What else could we measure?
We could do the volume once we put it down in there, or
What would we
before?
have to do in order to do that?
Okay. So we could measure what's the volume of a cylinder?
Well, we've got water in there right
or do you
now.
mean?
We've got water in here right now. We're going to lower this all the way until it's
so the
submerged.
displacement, we can get the volume using the displacement, and then we can do
So I guess we should find the.
initial.
So I'm going to call that about. Let's see, that's 8. I'm going to call that 805 milliliters. So that's V1 is 805 milliliters, and that's about all we can observe first, right?
Yeah.
All right, so let's go
Down into the water.
Come on.
Graceful. All right. So now it's completely submerged. Oh, nice. And you've also got the top part in there.
Well, you know, it's all works together to make 1 kilogram.
Yeah. Okay, so what's this new reading at then?
What do you want to call it?
So it's 9, 10, 20. We'll call it 930.
Right on the bunny? Is that the bottom of the meniscus?
It's like 928.
928
Yeah.
milliliters. Okay, what else could we measure?
Well, so now we could do density,
Well, we're not there yet.
mass and volume.
That's a calculation.
Oh, what else can we measure? Oh, we can measure. So this is different now. The weight is different. So now
So
it's
that's 8 point, let's call it 8.5 or 8.6.
yeah.
So the force wet is 8.5 newtons. Okay?
Interesting. Okay.
All right. So draw a free body diagram of the mass before and after and all the forces acting on it.
Okay. So before, it's just gonna involve the force
got
of gravity down, and then the force of tension up.
I'm going to call it
Or the FUP. I know it's not a string.
Okay. And the force of gravity down before was 9.8 newtons, and the force up is 9.8 newtons. Okay, so this is before.
Wait, don't we have to multiply that bottom one by the mass though to get the force of gravity? Oh.
Well, how did I know this?
Oh, on the scale.
Because the scale. So the scale is pulling up with 9.8 newtons, so the force of gravity is down 9.8 newtons.
Yeah.
And
Oh, I see.
So we're making measurements rather. We'll get to calculating pretty soon.
Oh, I see. Okay.
Okay, this is before, and this is. So now
It
the
was.
FUP is 8.5 newtons.
Yeah.
But how much does the force of gravity acting on the mass change?
No, it's still 9.8.
So we've got force of gravity is 9.8. So we're missing something. What direction is the thing we're missing? Is it up or down?
It's gonna be up.
So we've got something mystery force. And
Mystery
how much
force.
is that mystery force going to be?
1.3
Excellent. 1.3
newtons.
All right, you will come back to this
All right.
in the regular class. All right, now this is taught on a Thursday.
Oh, okay.
And then on Monday, they have to give me a piece of paper that explains the change in the scale's reading when the mass is submerged. We don't know why it is yet. Okay?
Da-na-na-na. Choose a cube and measure and record these things.
Okay, so
Should we get another whiteboard?
the side length. Oh, that's not a bad idea. I like that.
Whiteboard. And here we go. I will put it over here for you, Boykin.
Alright. So the length of one side is 3.19 centimeters. So 3.19 centimeters. Hello. 19 centimeters, which is 0.039 meters. Okay, the face area. We need us a calculator.
So times 2?
Area is going to be 0.039 times 0.039. That's 0.001521 meters squared. A square meter is a huge thing, so that's not very big. The volume.
So that times that. So it times it 3 times.
Yeah.
Could you also cube it?
Times 0.039. Well, I get
Yeah, you could just multiply it.
volume is 5.93 times 10 to the negative 5 cubic meters. Now, that's a good question. Could I also cube it? So 0.039 math. Where's the math button? There it is.
Oh, math. Oh, yeah.
Math. Hello, math. Oh,
Oh.
there, this thing's. And then 3.
Oh, crusty.
And I get the same
There it
answer.
is.
Okay, so there's a volume. Math. How can we find the math?
Scale.
Yeah, I screwed up. I should have had this.
It's okay. I've got one right here. Good thing I never put that away. I probably should be.
Bring a little friend along with us.
Come on, little guy. Get out of there. Ideally, it's 1 kilogram, but...
No, it's not.
Oh, sorry, it's a cube, not the...
All right, what did I do?
Oh, it's over there.
Aha! It's like, where are my glasses? Okay, and the mass is. Oh!
This one doesn't... I thought this one was the one that...
It has a maximum. It goes up to 200, and then it stops at about 250.
Should we go grab the other one?
The
The heavy-duty one?
I'm gonna cheat here, and I'm gonna say it's 285 mass equals 0.285 kilograms, and that's just a guess. It's,
Yeah,
right.
it is what it
Okay,
is.
so the weight would be
Mass times the gravity.
0.285 times 9.8. That's 2 points. So the weight is 2.793 newtons, and I can't use that many significant digits. I'm just going to call it 2.8 newtons because I'm making this up.
Yeah.
All right, and the density. Well, how do you, and this density is how much stuff is in how much volume.
Mm-hmm.
So,
Density
in
would
the
be...
here's our Greek letter rho again.
Yeah, I saw that and I was like, they're using it again.
How much volume? So rho is equal to 0.285 kilograms divided by 5.93 times 10 to the negative 5 cubic meters. 0.285 divided by 5.93 times 10 to the negative 5. Woo!
And we get
4806 kilograms per cubic meter. So if you've got a cubic meter of this stuff, that's going to have a tremendous mass because a cubic
big old thing.
is huge. All right. So page 308, number
1 and 2. Oh, book right here? Oh. Oh, old book.
Oh no, it must be the, oh, you know what, I bet it's the regular physics textbook.
Good thing we've got them everywhere.
Although we really don't need to do these.
Is it just density?
Well, I don't know what the deuce.
Can we go back over there? That's 6 and 7.
Huh. I wonder what the heck. Well, maybe it is the new textbook. Because I did have this at home when I did this.
308.
It is.
Mm-hmm.
Okay, so we'll just read them. And I don't want to insult you. One of the concrete pillars supports a house is that tall, has a radius of that much. The density of the concrete is about that. Find the weight of the pillar in pounds. So you want to find the weight, you got to find the mass. So they give us the density, and from the radius and
You can find the volume
we
of
can
a
find the volume,
cylinder?
and so you just solve for the mass.
Yeah, okay.
Okay, a cylindrical storage tank has a radius of that. It's filled to a height of that, so we can get the volume. And then it holds that many kilograms
Oh, yeah,
of a
it's easy.
solvent. What's the density?
What is the equation for volume of cylinder? It's like 3 or 4. It's some equation.
I think it's 4/3.
4/3 pi
Well,
r.
no, it's pi r squared h.
H, is that right?
Yeah, because
Yeah.
you've got the area at the bottom.
Yeah.
And then how high.
Oh,
it is.
yeah. That makes sense.
Pi r squared h. All right.
Yeah, it's working. Okay.
All right, so.
Where'd the clicky thing go?
Clicking.
Oh, there. Right.
Yeah, there it is. All right, so now.
Okay.
I'm
Oh, this way? Hold a cube in your hand and notice how it feels. Ooh, heavy.
Okay, all right.
Quote, heavy.
Now, tilt it up so that one point rests.
Oh,
Feel the difference?
yeah.
Okay, why?
There's not as much. It's less pressure. I cheated and looked at the notes. But there's less area on your hand. You know.
Okay, what is pressure?
What is pressure? Did you
Why
see my
is
text to
stiletto-
you yesterday?
No, I didn't.
I was looking through it. I saw this and I was actually working out and I was like, ha!
Well, and here's the thing. In self-defense classes for women that were taught back when I remember in the 70s, they had a thing that if someone comes up from behind and grabs you and you're wearing stiletto high heels, you raise your hand, you stamp the heels.
God,
on there,
it's literally a dagger.
and what happens, it will punch a hole in their foot. And if that doesn't work, you just rip it along the front of their shin.
Ah, God.
And it'll open it up to the bone.
Oh, God. Gross.
No,
I'm
no,
like,
hey, women,
yeah.
gonna mess with you?
Yeah, I know.
You're gonna mess with them.
Yeah.
So,
I'm always
and
telling
so-
Justin.
But why is that? Well, because of pressure. You had, when the cube was like this, the force of gravity on this stays the same.
Yeah.
And all that force is distributed over this area. When you tilt it up like this,
Less area, more pressure.
all that force, same force, smaller area, this is an inverse relationship. This gets larger. I beg your pardon. This gets smaller. This gets larger.
Yeah.
This gets larger. That gets.
You know,
smaller.
I never understood that in high school, and I don't know why I didn't understand it.
Because you didn't have me for it.
It's like not hard. Like
not hard.
I could not tell you what an inverse relationship was. I was so confused all the time.
And the thing is, there were lots of stuff like that I had a similar experience with. And I really didn't understand it till I had to teach them. Okay, so the units of force are newtons. The units of force are meters squared, square meters, and that is a Pascal. So the unit of pressure is a Pascal, and that's 1 Newton per every square meter. So if you've got a square meter and you have 1 Newton, is that a very large pressure?
A square meter?
If you
No,
have
a meter is
square
huge.
No, that's nothing. So a Pascal is a very small thing, and so as you know, for example, at sea level, atmospheric pressure exerts a force of 101,300 newtons on every square meter.
So meter by meter.
Yep.
Ooh la la.
Have you ever seen this demonstration before?
Yes, I think so. Does the can crunch in, right?
All right, yeah. So what I've got here is a can with a little bit of water in it. And we're applying a little bit of fire here. And what's happening inside the can?
Heat is being transferred from the metal to the water. Water is heating up.
Excellent, excellent. So what happens is the flame is directed to the can, and the metal heats up the water. And so when the water heats up, what happens to the water molecules?
They start doing more
They
dancing.
move faster.
Little
They move
little
faster
jig.
and faster. In fact, do I have? Oh, that's good.
Do I have enough in there? Oh, you can start to hear it a little bit there.
Okay, now they move so fast that the intermolecular forces can't hold them together, and so they dissociate. They move apart, they transform from a liquid to a gas.
I actually taught this in my calorimetry lesson last year.
All right, so, and what's coming out the top here?
It's the steam.
Steam. And so if I take this, I love doing that demonstration.
Cool.
Okay. Now the question is, why did the can crush?
It has to do with the temperature and the pressure and the.
Okay.
I
Well,
don't
what
exactly
happened to
remember.
the temperature of the? Because what happened as it steams, it pushes the air out, so
Yeah.
there's nothing in there but steam. And what happened when I put it in the
It
water?
condenses.
Okay, why does it do that?
Because it's colder and it goes from a vapor
It
to a
cools down. It goes from a vapor to a. All right. So and all the air was out, and all we had was steam. That steam condenses. Why did the can collapse? Is there anything on the inside pulling?
No. Oh, okay. So
Is there anything on the inside?
no, it's not pulling.
No, there's no little
It's the
handles.
outside pushing in.
That's right. That's
Yeah.
right. And that's because the sea level, the surface, the atmospheric pressure exerts a lot of pressure.
Yeah. So okay. So steam. So it heats up their steam. It's going out, and then when you put the can into the water, the steam inside. It's not fair to say everything's pushed out. There's still air in there, right? It's just moving.
Well, no, it is fair to say that the air is pushed out.
So the air is pushed out, and then at that point, when you put it back into the water, the air inside condenses.
Yep. Well, the steam can.
Sorry, so the steam condenses, and then at that point, it's cool. So it's cooler, and then again to explain. So why does the?
It's not that easy.
I don't have to sneeze.
Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to read.
If you can't
It
write,
undermines the
use
writer's
Grammarly.
message.
So the pressure is this gonna help explain a little more?
We're not going to go through the whole of this.
Giant, 70 feet long, 15 feet high, thick steel casing meant to contain things like fuel, even in case of a derailment. How could something like that spontaneously implode and crush itself? Well, if it did in fact happen, it had to do with pressure.
Whole ballgame. A difference in pressure. Filling the container with steam pushes out the air. But if the vessel is sealed while it's still hot, and then allowed to cool, the steam condenses, and the internal pressure drops, meaning the now much greater external pressure pushes in on the surface. And that's bad news for the can.
Oh, there we go. There we go. Oh, it's actively moving. Look at that.
Okay, now we're gonna stop this. All right, so at the end it shows the tank car big, and it's not on this video clip, but that was a real good explanation. I think.
Yeah.
All right, so going back to our little friend, the PowerPoint.
So essentially, the steam is heated. The water heats up into steam and pushes all the air out, and then as it condenses, it
goes from an
expanded gas to a liquid,
which occupies much less volume.
Yeah, but it's paired with the fact that the pressure is more on the outside as well, and it crushes it.
Well,
right?
there are two separate things.
Yeah, there's two
separate things going on. You got nothing. The air goes out because the steam pushes it out, and so it fills with steam. And then when you put this in here, it the pressure goes down because the steel condenses. It pulls water in, and the external pressure pushes us. There's two things going on.
That's what I was trying to.
What happens inside the can, which goes from a gas to a liquid, which much less volume, but so what? It can't pull on the cans. If we were in outer space and did that, it wouldn't crush.
Yeah.
But it's the atmospheric pressure. So
Gotcha.
here's some information. 1 atmosphere. The atmospheric pressure is 101 kilopascals, which is 1.01 bar. That's another 760 torr, and this is
I'm more familiar with that one.
Inches of mercury.
Yeah.
Okay, or 14.7 pounds per square inch. So a square inch will have 14.7 pounds. That is the.
I hate that U.S. system.
You know, it is what it is. All right. So there are some problems in the book that we could do in 336. 3 through 5. Person could not balance her entire weight on a pointed end of a single nail because it would penetrate her skin. How can she lie safely on a bed of nails? You ever seen her lie on a bed of nails?
Yeah.
The bed of nails consists of many nails driven through a sheet of wood so that the pointed ends form a flat array. Why is the bed of nails trick safe?
Wait, so what's happening?
You got a bunch of nails and you lay down on the nails. You ever seen anybody lay down on the nails?
I haven't actually seen them, no.
Okay, but you've seen pictures.
Yeah, I've seen pictures of
All right, so how come if you have one nail and you step on it, it'll go through your foot, but you have a bunch of nails and you lay down on
It's because your force is being distributed over that area.
a larger area. That's all there is to it. Okay, a method wait a minute.
Number, what were we doing?
4.
4.
You climb a mountain, your ears pop because of change in atmospheric pressure. In which direction does your eardrum move as you climb up?
Okay, so as you go up, there's less pressure, so it moves out.
Yep.
Okay.
And as you go down, there's more pressure, so it goes
in.
in. So that's why your eardrums pop.
Just like with the can.
A bottle of juice is placed sealed under partial vacuum with a lid on it with a red dot or button is painted. Around the button, the following phrase is printed. Button pops up when seal is broken. Explain why the button remains pushed in when the seal is intact.
Wait, let me read that again.
Okay, you got they can the stuff. You got a jar.
Yeah.
And it's got some air inside of it and whatever product you put. While it's still hot, they put the lid on it.
Oh, okay.
And then it's got a little button on it. Okay, when you're on the shelf, the button is down. It's got the lid that goes up and down. Why is the button down? And why do they say do not buy, or what does it say?
Well, it has to do with the pressure, but I'm not, I don't know. I can't.
So if it's down, where is the pressure higher, inside or outside?
Oh, outside.
And so what does it mean if the button is up?
If the button is up, that means it's been opened.
That's it. That's all there is to it. And then there are some problems here. This is just density. The ice in the lake is that thick. The radius is that much. Find the mass of the ice. And basically what you've got is you've got the density of ice. And the density
Circular, perfectly circular lake.
Exactly. Neutron star consists of only neutrons and its unbelievably high densities. Typical mass and radius for a neutron star might be that mass and that radius. Find the density of such a star. Okay, well, you got to find the, I think this is the 4/3 pi r cubed here. And for the volume.
Oh, because it's a sphere.
Yeah, so you got a sphere, and then you got the mass, you got the volume, and find the density.
Yeah.
And it's incredibly huge because you're going, it's just incredibly huge because you got a tremendous
28
mass.
there.
Okay, and then if a dime were made of this material, how much would it weigh in pounds? So there gives you the volume, and it's just an unbelievable amount.
Yeah. So when it asks for a weight, it's not asking you want. So when you ask for a weight, is it really? It's not asking for the mass, it's asking for the weight. So you have to take that density.
So
and
you get the
multiply it by
mass,
the.
and then multiply it by the acceleration due to gravity.
Yeah. Okay, that's what I thought.
Okay, number 10. An airtight box has a removable lid. There's the area of the box, a negligible weight. The box is taken up a mountain where the air pressure outside is that. The pressure inside the box is completely evacuated. What's the magnitude of the force required to pull the lid off?
Wait.
Okay, so what you've got is you've got a complete vacuum inside, and here's the pressure on the outside, and that's the area. So you got the pressure and the area. They want to know the force to pull the.
I see. Yeah.
So it's just.
I missed the first part of the sentence. Yeah, it gives you where it gives you the area. Okay.
And then number 12, United States currency is printed using presses that generate a printing pressure of that much. A $20 bill is that. Okay, calculate the magnitude of the force that the printing press applies on one side of the bill. You just find the area by multiplying this times this. That's the area, that's the pressure, pounds per inch. You got to divide it by inches, boom, boom.
Now, what do we have to convert anything? If it asks, does it want it in ATMs or does it ever? It doesn't matter. You can use any
What it
numbers.
is the purpose of this is there's a bunch of different ones.
Yeah.
And, if you want to play around with conversions, that's
No,
boring.
I don't.
Oh,
Yeah.
here you go. High heel shoes can cause tremendous pressure to be applied on a floor. Suppose the radius of heel is that. At times during normal walking motion, nearly the entire body weight acts perpendicular to the surface of such a heel. Find the pressure that's applied to a floor when the heel because of the weight of a 50-kilogram woman. So you
What
find
would the area be for that? So what would the the
you're
radius?
going to be
Is it
6 times 10 to the negative 3 meters.
And it's just a circle, right?
Yeah, and that's going to be pi times this squared. So when
Yeah.
you square it, that negative 3 is going to become negative 6. So you have this
Really
really small
small.
area.
Yeah.
And so what you're going to have is a really large
Yeah.
pressure.
Sweet.
All right.
Cool.
So
We need to differentiate what type of heel it is.
so that's the end of the first lesson.
Okay, and we're done.
Peace out. Liquids and gases are fluids. They flow. Now, if what I did is you pour a glass of water into another glass of water, and the water flows. You can see that, and then you take what is it? It's bicarbonate of soda, and pour vinegar on it,
Baking soda, yeah.
and you make carbon dioxide gas.
Yep.
And then you put a candle in a beaker and pour the gas, and you can't see anything happening, into the beaker, and as it fills up, put the candle out.
Yeah.
And that's a great demonstration for kids. All right, so they're flow. So we're gonna, and you've probably seen this demonstration before. Okay, now, what's going on here? How come the water isn't doing this?
Yeah.
Okay, what I did is I squeezed it.
Yeah.
And that's because the air pressure on the card is greater than the force of gravity of the water on the card, so it stayed in.
Okay.
Okay, so there, fluids, they flow.
Fluids flow.
All right, pressure in fluids result from particles in motion colliding with a surface. Okay, which brings us to the sim over here. And here we have, by the way, this is also Pivnert, but here's we can pump gas and put it inside the chamber. It'll measure the temperature and the pressure, and over here, it gives us a profile of the speed of the particles. So let's, and I'm gonna put in, okay, and so as they are in, let's put in another dose of air. Let's get more going on here. And notice that collisions are happening. There are collisions between the individual particles, and they're collision with the walls. And as they have a collision with each other, energy is transferred, and so they speed up and slow down. And here's a distribution of the speeds. There are some going very fast, not many, some more going very slow, but the average, you get kind of a curve here. That's called a Boltzmann distribution.
Okay, yeah. I've
Okay,
heard that
and
before.
now, and what happens is the some of the collisions are head-on, some of them are glancing blows. But if you have a collision with a surface like this, and it comes in and bounces like this, it exerts a force in this direction. And there's a component of the force in this direction. And there's a component of the force in that direction.
Yeah.
Okay, so the net result is the perpendicular, the force that is actually exerted is, well, and then you got another one that comes in like this, okay? And it has one like this, which has a component like this and a component like this.
Yeah. Oh, yeah.
This
okay.
cancels this out. And so the net pressure, the net force is perpendicular to the surface. Okay. So what
Gotcha.
causes pressure? It's the air molecules or liquid molecules or fluid molecules colliding with the walls.
Okay. So that's kind of cool. I never really understood why it was perpendicular with the surface there.
Yeah, and it's because, and
It's
you can see
vectors.
from here, you got they're coming at it from all directions.
Yeah, it's coming like,
You get it's random.
Yeah.
And this is the definition of the random thing. Oh, by the way, as long as we're here, let's add some heat.
Yeah.
Okay, we add some heat, and look what happens to the speed. It's moving in this direction,
The
get more
Boltzmann
like that.
curve, right, is
Yeah.
moving more that direction.
Yeah. The temperature's gone up, and so has the pressure. Doink.
Doink, doink.
All right. Okay. Pressure increases with depth in a fluid due to the force of gravity. Okay. You got gravity pulls down every particle in a fluid. Okay. And no, here I've got it. Allow me to demonstrate.
Yeah.
Put your little pinky finger under one book.
Okay. Okay, here we are.
Okay, take it out. Put it under two books.
Oh, more. Ah!
Take it out. Put it under three books.
Ah! Yee!
Put it under the bottom.
Oh, man. Ow!
Okay, so now, and you can actually, that's a great thing to do in the
Yeah.
classroom. So the pressure increases with depth in the fluid due to the force of gravity. You have more and more water on top of you, more and more books on top of
Yeah.
you. There's more gravity pulling down on all those particles.
I see. That makes sense.
Where's our Bill Nye here? And we're going to start at 44. That's good enough.
Bill Nye the Science Guy.
Brought to you by
Pressure!
Oh, Bill Nye.
It's a hovercraft. It's in development. Now, hovercrafts float because of pressure. Now, pressure pushes on air or water or anything. Pressure is what makes rockets fly. Pressure is power. Pressure is a pushing force in all directions at once. It's what makes blood go through our veins or air come into our lungs. Now take a look at this. It's our water pressure brick breaker of science. These two bricks are the kind of bricks you might make a sidewalk out of. And over there is a bucket of colored water. It's connected to a hose. And the hose is connected to this big plastic cylinder. Now right now, the pressure in the cylinder, the pressure in the hose, and the pressure in the bucket are all about the same. But if I raise the bucket way up, then the pressure down here will be higher because the weight of the water is pushing down. It's the same way you feel pressure on your ears when you dive to the bottom of a swimming pool. The weight of the water makes pressure. Now the pressure in here will push up on this big plastic disc. And the plastic disc has so much area that it will create a lot of force. And that force will go up this metal rod and into these bricks. Okay, let's hoist the bucket.
He's doing work here. Increases the potential energy of the water.
Now, the pressure is going down the hose into the bucket,
He's reducing the space there,
pushing on the bricks.
increasing the pressure, you know?
Yeah.
It broke. Would you want them both to fall off?
Yeah.
Well, fine. Get them both to, we can do that. To fall off. The water is still coming down, pressure's still pushing up, and bricks just about out of water. And this is the first one, boom, see, look, they broke. But didn't quite break it because see, we ran out of water over here. See, that's all air. Ah, it's all air in here. No, I'm not mad. I'm not gonna like go nuts or anything.
I love Bill Nye.
Me too. Like,
right.
I can actually watch him, you know?
Well, and see, the thing is it's good science.
Yeah.
And I have, since my first year teaching, I always use Bill Nye. So pressure increases in depth of the fluid due to the force of gravity. So as he brought that bucket up, that increased the pressure down at the bottom of the hose. And as the water flowed, that pressure at the bottom was enough to push up on the...
Yeah.
So that's where we're going with this.
That makes sense.
Boom, da boom. Okay.
Okay.
Pressure at depth depends on the density in the fluid and the height of the column. So the above a point. So we've got rho GH. This is density. This is the acceleration due to gravity, and that's height. So
Looks a lot like MGH.
density is how much mass and how much volume, right? And so you've got mass over volume times the acceleration due to gravity. That's the force over the volume times the height. Okay, and so
Wait, sorry. Go back again. Sorry.
So what I've done is we've done rho,
Yeah.
then we added G to it, now we're adding H. So rho is mass over volume, you add G to it. Well, what is M times G? That's the weight, that's the force divided by the volume.
Gotcha.
And interesting thing, what is volume? Volume is length
Times width times
length
height.
times length. Okay. And then you've got, so this is
Length times
length times length, and height is a length.
So that cancels.
So what do we got? We have
Force over length squared.
force over area.
Oh, yeah. Okay.
So the pressure at depth depends on the density of the fluid, and here's the weight of the fluid per unit volume, and then you multiply it times this, and what you have is pressure.
Yeah. That makes sense.
Yep.
So this is just the how.
Yep. So what this does is this is something that exists in nature, and we're just describing how it works. And you say it's the same thing about books. You put your finger under more books, the height increases, and the density stays the same. The acceleration of gravity stays the same, but as you put a greater height of books on top of you, that pressure increases.
I've never learned it like that.
I know, sorry.
That's cool.
Okay, here, this absolute pressure at depth. Okay, here is today's one of today's two big ideas. All right, absolute pressure at depth. You've got here's water, and you are at this point some height of water above you. Okay, so you have the pressure of the air pushing down on the water, and I call it here the pressure at the top.
Oh, okay.
That's the pressure at the top. And then here's the pressure due to the H2O, which is rho GH. So this plus this equals the pressure at
Oh,
the
that makes
bottom.
sense. I was trying to understand this yesterday when I was looking at it. I was like, what? And I couldn't figure out what the rho was.
Well, and see, what is a lesson?
Yeah.
You have the basic ideas, and then it's your job to
Yeah.
explain what's going on.
That makes sense. Whatever the pressure is at the top, the air here,
Yeah.
and the density of the material, not the density, but the pressure of the material, which is which is that equation.
Yeah.
Is gonna, you just add them together, get whatever is at the
So
bottom.
what you'll see on the AP test, which we don't have anymore, is I've just moved these around.
Yeah.
Here's the pressure at the bottom. And here's the pressure due to the water. And that's just the pressure.
Wait, which one's the top? Which one's the bottom right there? Oh, okay, good.
Well, all I did is cross these.
Yeah, okay.
And why did I do that is because at the time in the AP physics equation sheet, this was the equation students were given.
Okay.
So this you can understand, right?
Yeah.
That's that thing over there. This is what they give you. And so one of the big things with AP is,
Be able to decipher.
yeah, but it means the same thing.
Yeah.
Okay, gauge pressure.
Wait, go back for a second. How come it isn't, if you're putting this over here, why aren't you subtracting it? Is it just,
Oh, you know what? Thank you.
Yeah.
I'm glad somebody's got a brain in their head this morning. No, what I've done here is I've inverted.
Okay, that makes sense.
This is the pressure at what you're looking at.
That makes more
And
sense
this-
that this is the initial top one. Okay.
See why it's important for student staff questions? Teachers never make mistakes. All right, and thank you. Because as I was explaining that, I was thinking, P original, that's like the pressure.
Yeah. And I was like, why is there no negative?
Yeah.
Okay.
Okay, gauge pressure. Now what is that? If you have a pressure gauge, you've got this little device that measures pressure.
Like on an air pump or something.
Yeah, and you've got this down here. That gauge pressure is rho GH, because when you take it up in the atmosphere, it's going to read 0. Okay, you got your measurement gauge up here in the atmosphere. There's no pressure. It's 0. Look, it's 0.
Yeah.
But as you take it underwater, there's more and more pressure. And what it's doing, it's not measuring this. That's called gauge pressure. Now,
So the gauge is not measuring the air, it's measuring the pressure of the
at that
material.
particular moment.
Yeah, of that material.
All right. Let's see.
My phone's not used to doing this much recording.
Oh, you're running out of gas?
I don't know.
All right. So let's show an example of that.
I know this side works. That blade's tripping.
It'd be tripping on you.
Oh yeah, I don't know what's going on.
All right. So there is something called. You've heard about manometers, right?
I don't think so.
A manometer is here's a form of manometer. In my chemistry lab, first chemistry lab at Merced College, they had one of these on the wall. It's a long glass tube in a tub of mercury. Okay, they fill the tube up completely with mercury, put their finger over it, and then immerse it in the fluid in the other mercury. Well, mercury is heavy; it's a metal, and it pulls down and leaves an evacuated portion. Because now, why is that? Well, because it's the air pressure that supports the column here. It's like when you drink stuff out of a straw. What are you doing? Here, take a drink from that. How did you do that?
You are sucking up, so
Yeah,
it's
and
like
how are you doing that?
by breathing in through my lungs.
Okay, you're not taking the water into your lungs.
No,
No, you
it's
close the
air.
back of your mouth,
Yeah,
right?
Yeah.
What are you doing with your mouth? Take another one. What are you doing with your mouth? You move
I'm
your tongue
changing.
down, right?
Yeah, I'm changing the how much space is in there.
You're changing the
Yeah.
volume.
Yeah.
So what you're doing is you're increasing the volume that lowers the pressure. All right. Well,
I'm increasing the volume in here, lowering the pressure. in
no,
here.
no, no. In your mouth.
Oh, okay, okay.
Your mouth has a larger volume that lowers the pressure. Pivnert, right? Mm-hmm. Okay. Everything is sealed except for this. You increase the size of your mouth, that lowers the pressure. And the air pressure pushing down on the surface of the water makes it go up. If this were perfectly sealed and no air could get in, you couldn't suck the water up.
Yeah.
I wish I had that as a demonstration, but I don't. Okay, but you have to do that. Okay, so this is a manometer. Another example of a manometer is, and they used to have these when I was before you were born. They'd have the cuff, and then on the wall would be one of these, a manometer. And as the pressure inside the cuff changes, they're measuring your blood pressure, we don't need to talk about that, would change this, and it would make this go up and down. Higher pressure would make this go higher. Lower pressure would make this go lower. And so they would measure that blood pressure off of this in inches of mercury. You probably heard that. All right, so this is another example of a manometer. And this, let's see, and well, no, I'm not prepared to talk about that, but this is how these things work.
Yeah.
And
So it has to do with so the manometers they measure the pressure, and
the question is, how do they do it?
Yeah.
It's because if you push harder on this, it'll push this up. If you push less hard, it comes down.
Yeah.
Okay, now, and there's a vacuum in it. Now, there is some mercury vapor, a small amount, but not much. And with this example, you have a certain pressure inside here that's larger than the atmosphere, right? A higher pressure than the atmosphere.
So it
you got
pushes it that
atmosphere
way.
here. Guinness más macho. This is more strong than this, so it goes down. And
okay.
this height here, you would read that's called gauge pressure.
Okay, yeah. Okay, that makes sense. Wait, could you explain this one more time? I think I finally get it. So the idea is
So you have
mercury,
you have a vacuum in here.
vacuum.
That doesn't want to let it out.
Yeah.
You know, it's like if you have a straw and you fill it with water and you hold
Yeah,
your
you
finger
hold it
over
right
the
there.
top, the water stays in.
Yeah.
Okay, well, the water stays in. All right, well, what happens if you take your finger off, the
It
water
falls.
comes out.
Yeah.
And so this is like having your finger on that, the mercury can't go down.
Yeah.
But because it's so heavy,
It,
the air pressure can only push up so hard. And so it's the air pressure pushing on the surface of this
Okay.
that determines how high this
oh,
goes.
I see. That makes sense.
What it does, it's kind of like helps it go up or come down.
That makes sense. So depending on how much air pressure you have that day, this will go up or down.
Yeah.
Depending, and this is the gauge. This is the gauge. That's what when you say
Yes.
gauge pressure, right?
Yeah.
Okay,
Yeah.
that makes sense.
All right, now I realize I left something out. Yeah, I'm not going to talk about it.
Not important.
It is important, but it's too bad. We'll talk about it later. Okay, let's take a look at some free response questions.
Sweet. Should I pause? Or are we gonna talk?
Pause, unless.
Play with density. Got it.
And density is a simple thing. It's just how much stuff takes up how much space. How much stuff, how much spot. Stuff, the units of stuff is kilograms, units of space is meters cubed. Okay, if the density of brass is that much, what's the volume of 1 kilogram?
That.
That's,
Oh, the 1 divided by that.
So rho is N over V. So V is N over rho. That's not V.
So our mass is 1, and our kilograms are 8470. Oh wait. Okay.
So we got 1 kilogram divided by 8470 kilograms per cubic
Oh yeah,
meter.
density. Sorry. Over there. I'm confined by my charger.
Oh, that's cool. We can stay right here. So we've got 1 divided by 8470. I had to look to make sure I can't read. So I got 1.18 times 10 to the negative 4. So I got, so volume is 1.18 times 10 to the negative 4 cubic meters.
Mm-hmm.
All right, so that should be the volume of this thing right here. Maybe you got a feeling for where we're going. Okay, how much did the water level in the graduated cylinder change when we immerse the kilogram?
1.3, right?
So the water level before was 805.
Oh,
and
shoot,
then
no.
went up to 928. So we got 928 milliliters minus 805 milliliters. 8 minus 5 is 3, 2. It's 123
Milliliters.
milliliters. All right.
1, 2, 3.
We good? We haven't lost anybody yet?
Nope.
Okay. If 1 liter is that many cubic meters, and 1 liter is 1,000 milliliters, how much is that in cubic meters? So I got
1, 2, 3.
1, 2, 3 milliliters times milliliters
100 on the bottom.
is 1,000 milliliters. Thank you. Is 1 liter times
1 liter.
1 liter is 0.001 cubic meters. So I got 1, 2, 3 times 0.001 divided by 1,000. I get 1.23 times 10 to the negative 4. 1.23 times 10 to the negative 4 cubic meters. So that's the volume of H2O displaced.
Sweet. That makes sense.
All right. Okay, now we got, if the density of water is 1,000 kilograms per cubic meter, what mass of water is displaced?
All right. Then we just.
So that's this again, right?
Yep. So we put 1,000 on the bottom, and for that 8470 number.
Okay.
Oh wait. Oh no, it's
No,
not.
no, no.
It's-
You may be right. So what we want, if the density of water is 1,000,
We want the mass
and we want the mass, that's going to be density
times. Oh yeah,
the
yeah.
volume. So this is, I'm going to do it right here.
We're running out of space over there.
Volume is 1,000 kilograms per cubic meters, and we've got 1.23 times 10 to the 4, 1.23 times 10 to the negative 4 cubic meters. I'm going to end up with kilograms here.
And that's for your mass, right?
Yeah, we want to find the mass of the water
Mm-hmm.
that's displaced. So that's 1,000 times
Is it going to be
1.23
negative 1?
times 10 to the negative 4. That's 102. Wait a minute.
Is that right?
No, I screwed up. Let's see. We want to know the mass. That's the density times the volume.
No, I think that's right. But did you plug it in your calculator right?
no.
Shouldn't it just be move it
should be
over?
one, I did 1.02 times 1.2. Good Lord. Times 1.23 times 10 to the negative 4. 123.
Yeah, that makes sense. And then also not V over there, but mass on the left side on your equation.
This,
Right? As I was like, wait, we're talking about mass, right?
So the mass of the water is
That makes sense. 123 grams or kilograms?
kilograms. It's 0.123 kilograms.
Oh, 0.123 kilograms. Okay, that makes sense. I'm like, it can't be.
123 kilograms.
Well, it can't be 123 kilograms.
So this is the H2O.
Mass, yeah. Sweet.
How much would that water weigh?
Multiply by 9.8.
Yeah. Times 9.8.
Picks up calculator again.
123 times 9.8. Yeah, 1.2 newtons.
Mm-hmm.
1.2 newtons.
What's next? We're on the edge of our seat.
What was the difference in the force measured by the spring scale between the drive?
Oh, 1.3. 1.2, so they're the same number. Okay, so hold on. So that means that the mass of the water.
Okay, where did this number come from? This is the mass of the water, right?
Yeah, that's the mass
How
of the
did we
number.
get that?
So
well, we
we-
had to find the volume of the water.
Uh-huh.
But what volume? That was the volume of a kilogram of
Oh yeah.
lead.
Mm-hmm.
I mean brass.
Yeah.
So this volume is this much, and then we converted that into, and then we did, well, how much did the water go up? It went up 123 milliliters. So the water went up 123 milliliters. How much does that weigh? Well, it's 1.3 newtons. Now hold up. What the heck's going on here? The buoyant force is exerted on all objects.
I've never understood buoyancy. Our mystery force is our buoyant force. Okay, and so
Okay, so the mystery force is our buoyant force. How did we get? We ended up with 1.23, right?
yeah.
And what is that? That's the weight. We got the weight from the mass, and we got the mass from the volume, right? Went from volume of water that went up.
Yeah.
How much did the water went up and with that much volume?
Okay.
Well, what's the mass of that much volume? You know, first we had to convert it into cubic meters. What's the mass of that volume? And then what's the weight of that? Well,
Okay, yeah. So we took the density of
So
water times the
water
the
went up
volume
this
of water.
much. How much does that much water weigh?
Yeah.
Well, it weighs this much.
And it makes sense to you that you'd multiply it by the force of gravity because we're talking about the force here. Okay, that makes sense.
All right, well, let me be careful here. I don't want to skip it.
We're telling the difference in milliliters. We converted that to meters squared.
Okay, so now that's the buoyant force, and
Yeah.
here's Archimedes' principle.
Ha! Archimedes.
The buoyant force equals the weight of the water displaced.
Okay.
The buoyant force equals the weight of the water
Oh, why didn't you just tell me that in the first place? What? That's cool. Okay.
Well,
We got to get there.
I could just tell you that in the first place,
That's lame.
but this proves it.
Yeah. Totally cool.
Okay.
So whatever the weight, so the missing force is the weight of whatever much water was displaced.
And so this part of the lesson is on Monday. So on Thursday we did the activity,
Is this for AP or for regular?
AP.
Okay.
and then their assignment was by Monday, by today, have an explanation why
Yeah.
the thing changed.
And then we go over it today.
And so maybe they have something, and then they turn it into me
Yeah.
at the start of class, and then we explain what it is.
Yeah. Gotcha.
All right, now
Bill Nye the Science
this is
Guy.
this is the best Bill Nye.
So we're talking about, so when you talk about boats floating,
Yes.
I don't have a question, but but I've always been a little confused about how boats float. And it has to do with the buoyancy, the water displacement, and the weight of that water.
All right.
And
All right, here we go.
Okay.
This is, what did I just do?
they really want me to buy a Quest bar. I'm allergic to those. They just don't know that yet, unless they're listening to me.
This is the best Bill Nye of all time in terms of help.
Sure is big.
I hope it floats.
It's a little late to worry about that now. Five me.
Bite me.
5 me.
Oh, bite. I thought you said bite me.
Yeah. Well, this is from the early 90s, so 5 million. Wait for it. Wait for it. Here it is.
Inertia is a property of matter.
Okay.
Inertia is a property.
Whenever I ask the kids like in the beginning what inertia was, they're like, it's a property of matter, and I'm like, oh,
How do they know that?
Bill Nye, the brainwashing.
That's right.
Disney presents Bill Nye the Science Guy. Brought to you by Boats. Boats float. Thank you.
You know, the reason that things float or sink is because water is heavy. That's right. The weight of water is what makes things float. Either big, heavy metal ships or small, heavy metal cars. Oh, here, put this on.
Oh, and saltwater is more dense too.
I gotta turn down this alley here. Hang on.
That's cool.
It's called an amphicar.
Buoyancy's a great thing. It's holding us up right now.
That quality.
Let me ask you something. You, me, and this boat are displacing water. How much do you think that water weighs? It weighs the same as we do.
Water weighs the same as we do.
Imagine this. Whenever a boat's in the water, it pushes some water out of the way. We say it displaces some water. See, place away. You with me? So it's as though this model
Got this boat
of
sitting in a
science
block
making
of
hole in the water
plastic.
shaped like this. Now take a look. This is the aquarium of science. And it's filled right to the brim. As the boat settles in, it displaces some water. It runs over the rim, down the scudder, into the
Oh, I think
stream.
I've seen
Now, the model boat of science displaced this water. In fact, all boats displace water. In fact, everything you put in the water displaces some water.
When you get in the bathtub, the level goes up.
This is the water level of the dunk tank of science. Watch. Using the latest in dunk tank technology, I'm going to displace some water. You ready? 3, 2, 1.
See?
Pretty cool, huh?
Gotta love Bill.
I displaced some water, right? Just like the model boat of science. Now watch this. I'm gonna place the boat on the scale, which right now is in balance. Now the boat takes it out of balance. Now I'm gonna put the water that we displaced earlier
Oh, what a great visual.
I know.
other side.
He just does such a great job showing everything. It makes me want to teach the class exactly the same he's doing.
Hey, when I started teaching, I had 40 episodes of this on video
Yeah.
video cassettes.
It just balances. Now, watch this. Take the displaced water, take the water, put it back in the hole we had earlier. That's one. Here's the second.
It's such a cool topic.
I know.
It fits exactly. Isn't that cool?
It
I
is
love
cool.
it.
Yeah, that doesn't get any better.
So you know what's really cool is based off what I'm learning about physics this year, I'm definitely going to be tweaking my chemistry stuff to be a little bit more like preparing kids
All
for physics.
biology reduces to chemistry. Mm-hmm. All chemistry reduces to physics.
Mm-hmm. So I kind of want to, I have to go through because I teach a thing on density and like I want to include this. I mean, not this level, but you know that's an easy. Why do boats float? There you go. There's your unit question.
Yep. So the weight of the fluid displaced is the mass of the fluid times the acceleration due to gravity. And we did that
Right there,
right
yeah.
here. How can you find the mass of the displaced fluid?
Boom.
Find the volume of the fluid.
Mm-hmm.
Okay. So density is mass over volume. So mass, you just take the volume times the density. And did we do that?
Yeah,
we did that here.
Yeah, up top in the brown.
Oh yeah.
Density times the
Yep.
volume. The colors are important. Okay.
So the buoyant force is equal to the weight of the water displaced, which is the mass of the water times the acceleration due to gravity. And how do you get the mass of the water? Rho v. The density times the volume. Density times the volume gives you the mass. So the density of the fluid is rho, the volume displaced is that. And
it has to be on the right page. That's why I get so annoyed with it. Yeah, there you go. One more time. There you go.
that's it.
Woohoo!
So
Okay.
now,
Cool.
shown below are 6 different objects that have different masses and different volumes. These blocks are suspended at 2 different depths in the water by being hung by a string from a supporting rod. Okay, rank these situations from greatest to least on the basis of the buoyant force on the blocks by the water. What's going to determine the buoyant force on each of these?
The weight.
The weight of what?
The weight of the blocks.
No.
No, sorry. The weight of how much they needed to displace. No. Sorry, wait. Give me that chance. So it's the weight of the volume of the water displaced.
Yep.
So if you know that there's this many centimeters cubed,
So
you
what
have to
determines
convert
how
that.
much water is displaced?
The
volume.
The volume, yeah. So you need to convert that into meters cubed, and then you multiply that by the
So we
density.
have the volumes already calculated for us. Which is going to have the greatest buoyant force?
Hold on. So we said we need the.
What
we need
determines the
weight.
buoyant force?
Let me look at the equations again. The weight.
And the weight, well, let's go to this.
Yeah. And the weight is our density times our volume times gravity.
Okay, now, and what this is the fluid. It's not the thing. It's the water displaced.
Yeah, so it's 100 kilograms.
So that wait. So hold on a second.
Or 1,000, sorry.
So what determines what the buoyant force is on each one of these?
The density of the water times the volume of space.
The density of the water is the same everywhere.
Yeah.
So what's going to determine it? It's the volume.
The volume, yeah.
So we've got 40,
so
40,
biggest
40,
volume, the
and
biggest.
10 times 10. So which one, is there going to be a tie?
Yeah, these 3 will tie and these ones will tie.
Yeah.
Right?
So the most buoyant force is going to be this. These large ones, because they're all the same, because they displace more water, and it's the weight of the water that determines the buoyant force.
Yeah. Okay, so yes. So the buoyant force is determined by the weight. The weight is mass times gravity, but it's also the density of it. The density is all the same.
Yeah.
And the in case you're wondering what I'm saying, Val. And then the volume is our different, and then the gravity is all the same on them. So it's basically, can you look at that equation and understand what variable is changing?
So now, and the thing is, you look at this, and all of a sudden, there's a bunch of different things you could do right here.
Yeah.
We could do the measure of the pressure on the top, the pressure on the bottom, blah blah blah. We could do all of that stuff, but that's not what it's asking you for. All right. So
all 3 of these would be, the greatest, and all 3 of these would be the least.
Three objects of identical mass are attached to strings suspended in a large tank of liquid as shown above. Must the 3 strings have all the same tension? Let's take this up to the front.
Okay, I'm gonna bring this with me.
The hint here is the thup. The tension in the string is the thup. Okay, so must all 3 strings have the same tension, even though they have the same mass?
So the FUP is the FUP is not no. Well, so there's 3. There's
I agree.
We have to
The
look
answer
at
is no.
force of gravity, force up plus the buoyant force.
Yeah, so since they all have the same mass, the force of gravity is going to be the same for each. But what the question is what's going to determine this? The buoyant force.
Yeah.
Well, what determines the buoyant force?
Well, the density of it, the volume of it, and the
Well, the density of what?
density of the liquid. So that doesn't matter.
Yeah, it's the density of the water that matters, and so
But
that's
the
going to
space
be
it
the
takes
same.
up is different.
And so it's the volume.
Yeah.
So
again,
must
it
the string,
comes down to
must they have the
volume.
same tension? No.
No.
And why not?
I mean, it has because they don't have the same volume.
Yeah, because
they're buoyant
they
force.
could have the same volume, but they probably don't. This looks larger, that looks smaller.
Yeah. What does it say? The 3 objects of identical mass. Yeah, it just says the mass identical. So.
Okay. All right. Object A has a volume of this. They give us the volume and a density of that. The tension of the string to which the object A is attached is that much. Okay. Calculate the buoyant force on A.
Tension in the string is that. Okay.
Okay. So let's take a look at this. They give us the tension in the string, and they give us the volume. Okay, and they want this. So if we've got the mass, we can find the force of gravity, right? So from the mass, we get the force of gravity.
Yeah.
We got the tension of the string. How can we find the buoyant force?
We subtract.
Yeah. All right. So how can we do that? Oh, it's just this, which is the weight, which you can calculate,
Yeah.
minus this, which they give you. It's going to give us the buoyant force, right?
Yep.
And then calculate the density of the liquid.
Ooh.
So we've got the buoyant force here, and we've got the volume. So we've got the buoyant force.
Wait, no, we have the mass of the object. Oh, the masses are all the same.
So the buoyant force is equal to what?
We want the density, is it?
Yeah, we want the density of the liquid.
Oh, the liquid. Okay.
So we've got the volume of the liquid is the volume that's displaced
Which it tells us here. Okay.
by the volume. So we got the volume, and they want the density.
Oh, you could use this equation right here. So we're gonna go ahead and use the buoyant force, which we just didn't
Yep.
we just calculate that?
Yep,
Is
we
that
did.
what we did? We calculated here and we subtracted it,
So we got the buoyant force.
and then we can say the buoyant force, and we could solve for the mass right here, right?
Yep.
Or no, I'm sorry. We should probably use this equation right here because it wants the
Well-
density, right?
Yeah.
We could solve for density. So we say the buoyant force divided by the volume times
Which they
the,
give us,
times the wait. Do we have the the force of gravity?
and the acceleration due to
Acceleration
gravity.
due to gravity,
That's
sorry.
9.8 or 10.
Yeah.
So
And then
we
get
just
that.
take, and they want the density. That's just the volume acceleration due to gravity divided by this, right? You just take
Yeah.
those two and divide by boom to boom.
But it's next.
Okay, say this is object A, so we just did object A. Some of the liquid is now drained from the tank, so only half the volume of object A is submerged. With the tension in the string, right here, increase, decrease, or remain the same.
So it's gonna be.
So if the water level goes down, what's going to happen to the thump?
It's gonna be bigger.
Well, first of all, and why is that?
Because this is gonna decrease.
The buoyant force
Yeah,
is
because there's not as
decreased
much volume.
because you're not displacing as much water.
Yeah.
Yeah.
Okay.
How you doing?
Good. It makes sense. I definitely needed some practice using the equation. So it's about connecting it to everything. So
Here's a classic AP physics question.
okay. We got it's a lake? Is that what it's saying? It's a lake?
Okay. A large rectangular raft is floating on a lake. It gives you the density of the raft. Okay, the surface area of the top of the raft is that, and its volume is that. The density of the lake water is 1,000 kilograms per cubic meter. How high is it going to float? The height of the portion that's above the surrounding water.
Okay, so we just use
All right.
let's draw this bad boy. Oh, sorry, I took it away.
No, it's okay. So the buoyant force is equal to the weight of the H2O displaced.
Which is equal to mass times gravity, which is equal to
So hang on a second. And so the height, which is equal to the weight of the raft. Right? It's like what we saw in the Bill Nye video. That's the boat is equal to the weight of the water. So how can we find the weight? If we know the weight of the raft, we can get the weight of the water, and that'll equal a buoyant. Is that what they're asking for?
Oh, they're asking for the height.
Okay.
So I think we need to use the what's the one we had with the height in it? You know? Oh, the gauge one.
Rho GH.
Yeah, rho GH.
So density of water. No,
it's the pressure.
no.
That's pressure.
We're not doing that.
Yeah, I know.
I don't think so. Okay, so what we want to know is.
How can we figure out the height there?
Okay, so H is going to be a fraction of the.
On a raft. Okay, the raft has a density of that much. It's floating on the lake. The surface area at the top of the raft is that. Okay, so we've got the area, and its volume is that. We've got the volume.
Oh, okay.
The density of the lake is that much. So
okay, this height, the volume underwater is the area times the height.
okay.
So the volume underwater is the area times the height, because that's the total volume is the area of the top times the thickness of the raft. But we don't care about that. We just want to know what this is.
Okay.
Okay, so now let's see.
I don't understand
So
their
that
picture right
means-
here. So is the whole thing? I don't understand their picture.
So this dotted line is underwater.
okay.
Okay.
Oh, okay, it's the raft underwater. I see.
All right. So
Oh, it wants to know the height. It wants to know this height right here.
oh, above water.
Yeah.
Oh, I beg your pardon.
Yeah.
This is the height
Above.
under, and this the height above. And this is what we want right here.
Yeah. Okay.
All right, but so the density of the raft, row of the raft, is mass
Is it a perfect? It's a no, it's rectangular.
over volume. Okay, and the volume is the area of the top times we'll call it the thickness. The thickness of the raft. Okay, so that's the mass times the area of the top times the thickness.
And we're given that. We have the density of the. Oh, I need to.
Okay, and so what we want is from this is a hard one.
I know. I'm like, how do we? Okay.
Turn that off.
Okay. No, this is good.
What do we got here? Let's start over here.
Okay.
The weight of the water is equal to the weight of the raft. So,
Oh, we had that right there. we erased it. That's okay.
the weight of the water is equal to the weight of the raft. So, we needed to find the weight of the raft. Yes? And so the weight of the raft, we needed to find the mass of the raft.
Wait,
Okay.
let's work backward.
You want to go backwards?
Yeah, let's work backward.
All right. All right. So we found the total height of the raft
By doing
by
what?
taking the area and the volume. Because the volume is the area of the top times how high it is.
Yeah, length.
So you
times
divide
width
by
times
the
height.
area, you get the height. So the total height of the raft is 0.22. It's about that much. Okay. And we want, in order to know how high above the water it is, we need to know how much it is below the water. Okay. Well, we need the volume of the water divided by the area of the raft. That'll give us the height of the raft. That's exactly what we did a moment ago. And this is the height, I beg your pardon, this is the height of the raft below the water.
Where did we get that 1.17 meters cube number?
Well,
The volume of the water. That's from over here, right? Over here, Boykin.
Yeah, 8.2, yes. So where do we get the volume of the water? Well, that's the mass of the water displaced divided by the density of the water. How do we get the mass of the water? Well, the weight of the water displaced is equal to the weight of the raft. So if we can find the weight of the raft, we can find the weight of the water displaced. And if we know the weight of the water displaced, we can find the mass, right?
Yeah.
Because how do you find the weight? Mass times the acceleration due to gravity. So how do we find the weight of the raft? Well, you've got the density and the volume. So the density and the volume, we can solve this for mass.
Oh, we actually didn't even really need the weight. All we needed was the mass, remember?
All we needed was the mass.
So we just, yeah.
But the principle that allows us to do this is Archimedes.
Is that idea.
And so it's the weight, and weight depends on the mass.
So we took the pressure, which was given, and
Okay,
then
that's the density times the
Or
volume.
density, sorry.
So the density of the raft was this, and the volume of the raft is this, and so the
We got the mass.
mass
got
of the raft
weight.
is 1170. You multiply it times this to get the weight, but
And then we realized we didn't need it.
Well-
but it's the principle.
yeah. And so then the mass of the raft is equal to the mass of the water displaced.
Yes, that's the idea.
And so we had the mass of the water displaced. From that, we could find the volume of the water displaced. This is the volume of the water displaced. Divide that by the area, that gives us the height underwater. And so we got the height of the whole raft found by taking solving for this, and then the height underwater from all that stuff over there. So then you just subtract the height underwater from the total height, gives you the height above.
So this is a classic question, Boykin.
It's a bitch, isn't it?
Woo!
Principal researcher found the absolute pressure on the robot observation submarine and the level of the ship is about 413 atmospheres. The density of seawater is 1025 kilograms, so that's rho. And this, calculate the gauge pressure on the sunken ocean liner.
Okay. So let's write down what we have first.
So let's use this. So this is 413 atmospheres. 413.
The absolute pressure on the
Atmosphere.
robot observation submarine at a level of the ship.
Okay, now
to
that's
be
a good
that
question. Gauge pressure is what the gauge reads. Absolute pressure adds this.
Oh, okay.
So this is 1 atmosphere.
many. Oh, okay.
So you got 1 atmosphere plus this equals 413. So what's this? This plus this equals this.
Yeah.
1
Oh,
plus 1 is
412.
412. So this is 412.
Wait, hold on a second. Let me reread it this again. So while exploring a sunken ocean liner, okay, it's shown on the principal researcher found the absolute pressure on the robot observation submarine at the level of the ship to be about 413 atm, so all the way down there. The density of seawater is this much. Okay, so I see. And then again,
What's
so
the first question?
we always know that is 1 atm at top.
Well, it's the atmosphere.
Yeah, it's just 1 atm.
Yeah.
Well,
Now you could use that 101 kilopascals,
That's what I was thinking of, but it
101
gives you
bar.
413, so why would you do that to yourself?
Well,
Yeah. Okay, so first question says calculate the gauge pressure on the sunken thing. So we need those
just did
equations. Oh yeah, we need that one. That was right there.
so this is the gauge pressure.
Absolutely, that makes sense.
By the way, gauge is one of those weird words I always thought was gauge.
I've never been able to spell it. Okay, to calculate the depth of the sunken ocean liner. Oh, that's easy. We just use
All right, so
the
what
equation.
we've got here is that's this. We've got the density of the water, the acceleration due to gravity.
Yeah.
Just solve for this. It's this divided by this. The only problem is 412 atmospheres. We need pascals. We need newtons per meter. So 1 atmosphere was, let's see. we still have that paper.
101 kilopascals.
1 atmosphere is 101 kilopascals.
So we're just gonna multiply that by 101 and then
101 kilopascals kilopascals equals 1 atmosphere.
Yeah.
So we take this atmosphere, divide it by this. No,
You just multiply.
divide it by
Wait.
1 and multiply 412 times this, and that'll give
Yes.
us the kilopascals.
Yeah.
And then you just.
The rest is history.
All
Okay.
right, what's the next one?
Calculate the magnitude F. Oh, this is blurry. Calculate the magnitude F of the force due to the water on a viewing port of the submarine at this depth. If the viewing port has a surface area of 0.0100 meters squared. So calculate the force. Okay, so what's the force? You have to use that equation.
So they give us the area,
Uh-huh.
and the pressure is 413 atmospheres.
Okay.
That you have to change over to pascals.
Yeah. Okay, so it says, so let me envision what this is even like looking like. So calculate the magnitude force.
It's like your eardrum. The deeper in you go, the more the pressure on your eardrum.
Oh, sorry. Okay, I was thinking of a person standing above, but no, it's the submarine down there below. Okay.
You got a window.
Yeah, that makes sense. Suppose that the ocean liner came to rest at the surface of the ocean before it started to sink.
Okay, we're only doing it. We're not doing.
Oh, not that part?
The rest of those, yeah, the rest of that is
Okay.
accelerating.
Well, that makes sense. Well, that was pretty easy. Just gotta know what their terminology is.
The diagram, it's all about the way
Yeah.
it's explained to you. All right, here's another one.
Bada boom.
Here's the cheat sheet with the answer. Okay, a diver descends from a ship to the ocean floor at a depth of 35 meters below the surface. The density of ocean water is that. Calculate the gauge pressure on the diver on the ocean floor. So what we have to take is the air pressure, the rho GH. Oh, wait a minute.
We only need
No,
the
the
gauge.
gauge pressure is just rho GH.
Yeah, so they give us the density, right?
Density
And then we know the
Acceleration due
gravity,
to gravity.
and we know the height.
times that. Boom.
Boom. Okay.
And then the absolute pressure. How do we find the absolute
We
pressure?
just add 1 atm to
1
that.
atmosphere or 101 kilopascals.
Yeah.
Okay, the diver finds a rectangular aluminum plate with that, so you can get the area from that, right? A hoisting cable is lowered to the shift, and the diver connects it to a plate. The density of aluminum is that much. Ignore the effects of viscosity. What's the tension in the cable if it lifts the plate at a slow, constant velocity?
Okay, so acceleration is around.
We're gonna change. For any that the plate is equilibrium. So the tension plus the buoyant force. Oh, we
haven't learned about
Minus,
buoyancy
okay.
yet. That's the next lesson.
well, then, you know what? We're going to ignore that.
Okay.
We're going to stop right there. So that's just an opportunity to take what we did and
And the gauge.
see how easy it is the second time.
Yeah. Yep.
Okay, so once again, I'm not completely prepared.
That's okay, Boykin.
Looking for the ranking exercise. Yeah, you could pause that.
Forgot we've got more. Okay, so what was it? Calculate.
Calculate the magnitude of the buoyant force on the raft and state its direction. Well, we did that before. We've already done that.
Yeah, that's the weight. The weight of the water is the weight
The
of
weight of the water is equal to the buoyant force, okay? And then, we're not going to do this, but if the average mass of a person is that much, calculate the maximum number of people can be on the raft without it sinking below the surface of the water. Well, their total weight has to be less than this, equal to or less than this. So
divided by 75.
we're not doing that.
Okay, that makes
Divide
sense.
by 750
Oh yeah, 7 or.
because it gives us the weight.
Oh yeah. Cool.